Yeah.
Yep. Shall we start?
Are we supposed to see you, or are you just gonna show the screen?
Yeah. Can you see my screen?
Screen, yeah.
Okay, great.
Well, shall we wait a few minutes? Maybe more people will join.
Sure.
Oh, I see already more participants. Speaking of talking a seminar, now that we have kind of intercontinental seminar, I'm sure Piotr, Noah, you should speak too. And it's difficult to have you speak in the seminar when you're in a different continent, but if you can participate by Zoom, you know, sign up with Henry. Where's Henry? Still asleep? Okay, maybe we can slowly start. So today we have Konstantin. Tell us about, well, you can all see.
Yeah.
I hope you can all see what the title of his talk is, and so then, so.
Right. So, thank you. Yeah, I wanted to say that it's really great that this seminar continues, even though like all the circumstances. So, and thank you for invitation. Yeah. Anyway, so today I want to talk about this subject, which is Liouville quantum gravity, in its relation with other quantum gravities, for example, topological gravity, which for me will be mostly through integrable systems. And well, so this subject is not purely mathematical in the sense that Liouville quantum gravity it originated as a physical theory. So nowadays we know that there are many people, in particular in our department, who do Liouville theory using probability theory quite rigorously. But still, there are many things which are not completely clear. Anyway, I'll try to explain. Try to explain this connection. So let me start with formal introduction, let's say. So this connection is motivated by basically by the connection of different types of 2D quantum gravity. Oh yeah, and as always, please interrupt me, ask questions, and maybe make comments. So what is 2D quantum gravity? Well, so gravity, well, 2D gravity, let's say, is theory of metrics on a Riemann surface. And quantum means that we sum over all possible configurations. And I know three main approaches to realizing this physical idea of summing over all possible configurations. The three approaches. So well, one is the Liouville gravity. and I'll speak about it a lot today. Then there is topological gravity. And then there are matrix models. So today I won't speak, I guess, a lot about matrix models, but yeah, I'll tell the connection anyway. So in my my main goal is to give some kind of connection of this this Liouville gravity to these two approaches. So Liouville gravity. Yeah, and if I want to think about it informally, how it appears, how it arises, then it's not very complicated. So let's say we have some Riemann surface, sigma with a metric on it and some matter content. Let's say matter. So what it could be? It could be, for example, it could be a map from our Riemann surface to some manifold, or it could be, for example, let's say qth root of canonical bundle of our Riemann surface, and so this will be the case. Today. So, and in physics, like you know, if you want to do if you want to study some quantum theory of let's say these objects G and F, so of metric and matter, then you would construct some partition function, and this partition function would be realized as path integral over all possible metrics. So it's not genus, it's metric, Riemannian metric, and all possible fields, and then you weight it with the usual weight, which is action. So as, let's say, matter of F and G. So it depends on G because we're going to some covariant action, and then some gravity action, which depends on G. And so Liouville gravity is originally an attempt to take this path integral directly. So it's idea by Polyakov.
Konstantin, I had a question. So
yep.
When F is a qth root, you mean F is a section of that bundle or a choice of that bundle?
It's a choice of that bundle. So it's a choice of the bundle. So it's like F is line bundle, which is isomorphic to, whose qth power is isomorphic to.
I don't know if one can call it a matter because this is some non-local object on the Riemann surface.
That's right. That's right. Yeah. So in particular, there will be no action. Like there will be no action of the matter, but it still works as the conformal field theory. So because most of conformal field theories don't have path integral representation. Okay. So the idea of Polyakov is to separate the integration over say conformal classes of metrics. So it's a representative of a conformal class, let's say in G, and this is a conformal factor, and then the partition function becomes so some finite dimensional integral, some measure, and there is a path integral over the conformal factor of exponent of the action of matter plus action of Liouville, which depends on this phi. At the time, some Jacobian, which can be realized as phi df of ghosts, or any other way. So this S Liouville of phi is integral over a Riemann surface of the area factor, let's say, so with coordinates complex coordinate xi t to xi with the usual kinetic term for our field phi plus the non-trivial exponential term. So this depends on xi, of course. Okay, plus something else which is not really important. So why I wanted to write this formula is because it's called Liouville theory, since the equations of motion. So if I want to minimize this function, to find critical points of this functional, then other Lagrange equations tell that the equations of motion are just del bar of phi is equal to 2b mu exponent of 2b phi. So yeah, here I should maybe say, so mu is a parameter of our theory. Parameter of theory. You could think of it as a Laplace dual variable to the area of our surface. And this is a constant which depends on the matter, depending on the matter. Yeah, and so this equation here or here is just a classical, to some normalizations. It's a classical Liouville equation. So its solutions are surfaces with constant negative curvature. Great. So this was kind of the introduction. And now I want to tell a bit about how we work with Liouville theory. Well, there's the work of many people like the Aleshkin brothers. Let's see.
Question first. Is this constant b, do you have to find it somehow adjusted to make some contribution from the matter, or
exactly. So I'll talk about this a bit later, but it is determined by the matter, yes. So Wojciechow's, Dorn, Otto, Teschner, others in the late 90s, late 80s, early 90s. So they developed a CFT formalism, so conformal field theory formalism for the Liouville theory. So instead of like working with some Lagrangians and dim path integrals, we can do a CFT, which now is there are a few mathematical approaches to realize this CFT. But what I guess most of people here, if not all people here, know is that so a conformal at 2D CFT is completely determined by two pieces of data, by its spectrum and 3-point functions. The spectrum is the same as state space, 3-point functions. And then the formalism of conformal bootstrap or like operator product expansions can reconstruct the whole theory using these two pieces of data. So if I want to define a Liouville CFT as a CFT, then we need to understand its spectrum and 3-point functions. So, and what is different from most most CFT studies in mathematics, like for example, WZW theories, which lead to KZ equations, or minimal models, which lead to BPZ equations. So the spectrum in this case is continuous. So spectrum is integral over P, where times all real numbers, of the objects which I'll write and then define. So exponent of Q, let's say, plus 2IP. 2IP multiplied by phi. So what is this? So the notation stands for the same phi as we have here. So phi is a conformal factor, and the notation implies that it should be related with this conformal factor with some complex power. But technically, this is a Verma module. So highest weight representation of Virasoro algebra. Virasoro with central charge. So yes, 1 plus 6 b inverse plus b square. So here this parameter b enters, and the weight, which is called conformal dimension. So I'll call it delta p, delta Liouville p, q power 4, q square over 4, plus p square. And I didn't tell what q is, so q is just b inverse plus b. So anyway, so this b and q are two numbers which are related with central charge of the Virasoro algebra. This is a spectrum. Oops, sorry. So all the states of our theory are identified with element in either of these Verma models.
Konstantin, I thought at some point there was a big time conjecture that this is the spectrum. Or that has been proven in the meantime, or we assume it, or.
So at least in the physical literature, I think it's proven. In mathematics, yeah, it depends. I don't know. So for example, if I imagine a probability, people work with different fields which have real exponents. But yeah. So right, and then the 3-point functions. 3-point functions. Let's say, so we consider 3 fields, exponent of 2a1, phi of 0, exponent of 2a2, phi of 1, exponent of 2a3, phi of infinity. So these guys over here, those are vertex operators corresponding to the state of this theory, where this a is 1/2 of this exponent, and the vertex operator are inserted at certain points, and then this guy is given by the DOZZ formula. So yeah, I don't see much sense. So Dorn is Molotchikov. I don't see much sense in writing it, but it's a meromorphic function, meromorphic in A1, A2, A3, and B. Right. So, and this is the conformal bootstrap approach to the Liouville theory. So in particular, if I want to consider the operator product expansion of two fields, let's say these two guys, then we'll have the result will be integral over the whole spectrum of contributions from each particular vertex operator inside the brackets, multiplied by the DOZZ structure constant. Okay, so
do these structure constants also have some description in terms of Virasoro, or?
In terms of Virasoro, no. So the structure constants are like intrinsically some intrinsic quantity to a CFT. So which cannot be deduced from Virasoro directly. So they're related via what is called. So it's related to some some partition functions of for D gauge series, AGT, right? AGT to D gauge series. Some partition functions. So they can be represented as some infinite products which arise from localization for D gauge series. Anyway.
I guess, so maybe it's a slightly naive question, but it's the same vein as Noah's question. So in 4D gauge series, we'd like to think about these things. And then in particular, this kind of this of the Verma modules is not really Verma module over of the Virasoro algebra alone, but it's a module for some kind of some kind of big quantum loop group, and that of which the R matrix is this Liouville reflection operator. And then in particular, this sort of products of gamma functions, they come as also come as some some kind of vacuum matrix elements of yeah, they like has anybody on the Liouville side thought about this at all? Like, for example, if I write this kind of Liouville reflection operator, I actually solve the Young-Baxter equation. Is that a useful piece of information on the Liouville side?
Yeah, I think for instance, Ljosh Litvinov does something like this, but yeah, I don't know enough about this story.
Okay. Should
learn though.
Sorry, can you, where in the physics might there be something about this?
So Alexei Litvinov, like in some of his works.
Oh no, not that. No.
Why? Okay.
Well, I don't know. I'll explain you later.
Okay. Yeah. So right, that's I guess what I wanted to say about Liouville theory for now. I'll return to it later, but for now I want to explain the matter content. So for our theory, and I will use all the conformal field theory. It will be minimal models of CFT. So discovered by BPZ in 91, I guess. So actually, as far as I understand, these minimal models were, like in physics again, were discovered accidentally while trying to find CFT formulas in full legal theory. So this P stands for Polyakov. It's Belain Polyakov knowledge anyway. Right, so minimal models of CFT, those are much better understood conformal field theories. And again, for them, we specify the spectrum and 3-point functions. So then minimal models are associated, for a coprime pair, for coprime numbers, Q and P, there is a CFT corresponding minimal model. And the spectrum is discrete. So spectrum is discrete sum. Maybe right here. Of Virasoro representations. So Mn inside the table. And this table is called the Katz table. So it's table of size P times Q. And we count integer points inside. And each point inside the table corresponds to Virasoro representations. So this is actually so irreducible irreps of Virasoro inside the Verma models of some weight. Maybe I don't want to write them explicitly. And central charge is given by, so 1 minus 6 q inverse minus q square, where q is, maybe not q, q is a bad notation. Yeah, actually it's the same b, so it's fine. B is square root of q over p. So in this case, yeah, maybe one last remark about Liouville theory is that all of these Fermat models are irreducible. What is not true for these Fermat models? So these Fermat models have actually infinite number of Fermat submodels, and this contribution to spectrum are actually irreducibles, which are factors of the Fermat models with respect to all of their submodels. And 3-point function functions. So phi and 1 and 1, phi and 2 and 2. So this is big phi as opposed to Liouville's small phi, and 3 and 3. Again, those are vertex operators corresponding to this states in the spectrum. And this is what I'll call the n1 and 1, 2 and 2, and 3 and 3. So times structure constant of minimal model, which was found, for example, by Datsenko Fatiev in the 80s. Yeah, but the interesting part here is this guy over here. So it's 1 if fusion rules, so-called fusion rules, are satisfied. And 0 otherwise. And the fusion rules are basically SL2 like fusion rules for these indices. So if we treat these guys like say M1, M2, and M3 as spins, so like weights of SL2 representations, then the fusion rules are satisfied if let's say, maybe I'll write some formula. So it's equivalent to say M3 is 1 plus M2 minus 1 plus 1, and same for ends. So and have different parity, maybe. And sum of mi is odd. So yeah, those are correlation functions and spectra for these two theories. Now I can finally introduce the gravity. So let me maybe say before this say one more thing. So in general, correlation functions of CFT, steady minimal model, let's write something like this, and 1, zeta 1, phi m2 and 2, zeta 2, is some real analytic function functions of zeta i's, which are basically combinations of Hermitian combinations of conformal blocks and structure constants. So this is how the conformal field theory formalism allows to reconstruct all correlation functions using with coefficients given by structure by 3-point functions. 3-point functions. So yeah, now I can talk about gravity. So again, some physical works by Konjecture, Polyakov, Zamolodchikov, Dissler, Kawai, and other people. Why this works? People understood how to write correlations for gravity theory, whose matter content is minimal models, and whose and the gravity is given by the Liouville gravity. So what do we want to do for gravity? We want to get rid of all dependence on the metric. We want to get rid of all dependence on the insertions. So maybe I read the definition. So correlation number. So here's called correlation number because if we integrate all the insertions, it will not depend on anything, so it will be just a number. Correlation number of minimal Liouville gravity is, so the notation is the following. So I use this bold O and 1 and 1 up to, let's say, MK and K. And today I'll work in genus 0 and open genus 0. So where, again, these indices are from the cuts table. So, and naively, what do we want to do? So we want to take a correlation function of minimum of our matter content up to M, K, and K. So some positions. And then integrate over all of these positions. So this is moduli space of n punctured spheres. But this expression is not well defined because the conformal fields, so they have conformal dimension, meaning that they have the following coordinate transformation. So it has to be multiplied by something in order to be a well-defined density on this moduli space. And the way to do it is to multiply it by the corresponding correlation from the Liouville theory. And then take the integral over n-3 insertions, since we live on the sphere, and we can fix any 3 points to be, let's say, 0, 1, infinity. So where A1 up to AN, so indices of these Liouville fields, are defined by N1 and 1. There is some simple formula, which basically forces this expression to be a density, like density of a differential form on the moduli space of curves. So yeah, there are a couple of technical details here which I omit, but the whole point is that so what is the input of the Liouville gravity, minimal Liouville gravity? So the input is a minimal model, which is a CFT associated to a coprime pair of numbers, and the output is a set of correlation numbers. So for any let's consider the case of the sphere now, for example. So for any tuple of minimal model fields, we can associate a number which we call a correlation number, let's say on a sphere or on any other image surface. And this will be the data we are interested in. So as always, we can build a generating function out of this. Generating function. So I call this f Liouville q over p of the generating parameters. So lambda mn's, where mn lie in the cuts table. Size p minus 1 times q minus 1. Yeah, and this is just the generating series of these invariants. So exponent of sum, let's say, over mn in the cuts table, lambda mn, this O mn. So this object is a formal power series in p minus 1, q minus 1 over 2 variables.
That integral you wrote, that converges, right?
I cannot say in like in the most general case, but for example, up to 4 points it converges.
Okay. And what about in higher genus?
Okay, so this subject is today I want to concentrate on genus 0.
But in principle, do you think there'd be some divergences there, or this is?
No, I think it will be convergence. It's just convergent. It's just that the analysis becomes quite complicated, at least for me.
Okay.
So yeah, speaking about higher genus, so what's the main problem with this theory? The main problem so far is that we don't know much about these numbers. They are quite complicated to compute. So let me give examples. N equal to 3. Well, if n equal to 3, then modular space of 3 punctured spheres is just 1 point. So there is no integration, and the gravity correlation number is just a product of structure constants of the Liouville theory, A1, A2, A3, times the structure constant of the minimal model, so which is n, M1, M1, M2, and 2, M3, and 3, times this guy. And this turn out to be a very simple expression. So this is constant, which doesn't depend on anything, times this fusion rule coefficient of the minimal model, which is again representation of SL2 for each of triple of indices m and n, times just product of some normalization factors. They're called lag factors, which depend on these AIs. N equal to 4, it is first kind of non-trivial case. So this OM1 and 1 to OM4 and 4 is an integral over, well, modular space of 4 punctured spheres, which is just a sphere itself. So P1.
Sorry, Konstantin, I missed the AIs. They're also determined by N and M. So
yeah, the AIs are completely determined by
N and M. Okay.
There is some simple formula. They call it so. These guys over here are called gravitational tracings of the corresponding fields. So they're needed so that product of these two guys transforms as a 1-1 coefficient of a 1-1-4. Therefore, it's uniquely determined by M1, M1, etc. So for n equal to 4, this is integral over P1 of 4-point correlation functions M4 and 4. Okay, and so this in particular, such such integrals we can compute because we know that 4-point correlation functions are written using 4-point conformal blocks, which are well-studied objects. And these integrals, they can be evaluated numerically, so they converge. But also there is a work by Belavin and Aleshkin in, I believe, 2004. So in many cases can be reduced to 3-point correlation numbers. Well, and this is good because it's a kind of a recursion relation, which we would like to get in counting theories, because many counting theories and mutative theories, some complicated invariants can be reduced to simple invariants using some recursion. So in Liouville, so far there is no such general mechanism, even though like for 4-point functions, it partly was found, and later, like way later by me, and so this is Alexander Belavin and this is Volodya Belavin. I guess I think it was in 16. So we did this for all correlators in the when Q is equal to 2. But in principle, it's still an open problem. So, for example, for n equal to 5, 6, etc., this is an open problem. How to compute these numbers?
Is there a way to somehow not have something like a conformal block for the whole already gravity and the matter, or
unfortunately not, because like
usually in gravity, in series with gravity, it's easier to cut things because
that's right.
They're sort of topological in a way because you already sum over the metrics anyway.
Exactly. That's so the results are very easy, and in particular this recursion relations. The recursion relation is quite easy when it can be established, and therefore and precisely so. How does the recursion relation works? It works. It works basically reducing conformal blocks to this product conformal blocks. But here you see like this expression is a sum over conformal blocks, and this expression is sum over conformal blocks of different nature. And then you multiply these two sums, and so this is actually integral over conformal blocks. So a priori, nothing good happens. But the result, of course, is topological. The result, of course, is simple. And so there are some ways, though there are some ideas. There are some ideas how to do this. How to achieve this. So it's related with some relations between primaries in the Liouville theory and PPZ equations. It's called some higher equations of motion of Liouville theory. But and this is actually one of the big questions for me. One of the things I'm thinking about, how to solve this theory using kind of recursion. Okay, and yeah, basically that's it for a brief description of Liouville gravity on the sphere. So later, I hope I have time. I'll talk a bit about disk, where also some progress have been achieved. For higher genera, there has been not much work done. There is something about genus 0, genus 1, but yeah, so far it just is not studied enough. Also, as you'll see, so I mean, as we know, so in many theories, higher genera are determined by data from genus 0. So I want to have something like this for Liouville theory. So now I want to talk about topological gravity. So the thing I want to compare this with. So yeah, once again, so the object, the output Liouville theory is for a prime number. I have a formal power series in a bunch of variables. Oh yeah, maybe sorry, another thing which I forgot, which will be important for us, is that there is some scale independence. So all the correlation numbers, they depend on mu on this parameter mu of Liouville theory in a very trivial way. So it's mu power q minus sum over ai, or 2b, times the same correlation at mu equal to 1. So this scaling relation will be, oops, sorry. Okay. So this scaling relation actually will be important in the identification, because otherwise it's very unclear problem. So yeah, now I'm talking about topological gravity. And this is an idea which leads to much simpler computations, at least. So and the idea is again, so if we have a Riemann surface and with some data, then instead of summing over metrics, we can think that well, probably we don't want to consider theories which depend on trivial and conformal factors, so we can just sum over conformal classes. And so yeah, I will consider the following topological gravity theory, which is Q spin theory of Q spin curves. And so there will be a state space with a metric, so state space for R spin curves. So this guy is a vector spanned by formal vectors phi 1 up to phi, say, q minus 1. Then eta is a metric. Phi beta is, let's say, delta a plus beta q. And then the correlation numbers. So in topological theory, of course, we don't care about metric, about any associations. So the output of topological theory is just, in the old approach, I guess it's a bunch of numbers, which are called correlation numbers. More modern approach, it's some cohomology classes on modular space of surfaces. But anyway, correlation numbers are a definition. So Yeah, the usual notation for correlation numbers is something like this. So it's tau, some power d1, phi alpha 1, up to tau power dk, phi alpha k. So this is called a d1's gravitational descendant of phi alpha. And this is some integral over the moduli space of curves. Let's say G, genus G, mg and bar, of some class, CW of alpha 1 plus 1, etc. alpha k plus 1, multiplied by psi 1 d1, psi k dk. So, and this is this whole thing is, I guess most people know this, but it's some cohomology class on this moduli space of curves. And these guys are, so Chern classes, first Chern classes of psi classes, first Chern classes of a cotangent bundle at ith marked point, at one first marked point in this case. So there are some two forms into these powers, and this is called a Witten class, Witten's class, some cohomology class depending on this data. And right, so these are correlation numbers, and again we can make a generating series. For simplicity, I will work again with genus 0. So f0 1 over q. Yes, which will depend on infinite number of variables. So it's a formal power series, alpha k, where alpha enumerates elements in our state space, goes from 1 to q minus 1. And k enumerates gravitational descendants, so it goes from 0 to infinity. So yeah, this is just generating series. Sum, say, over maybe I'll call this d. The sum over k sum over alpha 1 d1 alpha k dk of these correlation numbers over there. Weighted with the corresponding coefficients, 1 over k factorial, alpha 1 k d1 up to t alpha k dk. So there is a column between those guys. This is a genus 0 of free energy, so this is a formal power series. In the variables, so t alpha d. For alpha d runs through, there is q times q minus 1 times infinity variables. And the generalization of Witten conjecture by the tablet. Okay, it works again. So generalization of the Witten's conjecture which was proven, for example, by, not for example, but Faber, Shadrin, and Zvonkin. in, I think, I think in 0.6. So it states that this guy is actually a logarithm of a tau function. So 1 over q over this is logarithm of tau function. It's of the dispersionless qth Gelfandicki integral hierarchy. So here I want to make a couple of comments. So first of all, if I want to consider all genera, it's, of course everything holds true, but it will be log tau function of the whole Gelfandicki integral hierarchy, not just dispersionless. I'm just focusing on genus 0 because yeah, there is not much done except for genus 0 for Liouville. And yeah, so this qth Gelfandicki integral hierarchies are certain generalizations of KDV. They're sometimes called QKDV hierarchy. As you can see, there is Q minus 1 set of times as appears in KDV hierarchy, or Qth reduction of the Kandom-Tsepetuashvili hierarchy. So let's see. Yeah, maybe just a couple of words about the hierarchy. So how to? So yeah, and what I want to say is that this generating series, which encodes all the animative invariants of this Q-spin theory, of course, has a lot of structure. There are many topological relations between the invariants, and there are several ways to encode these relations. So in particular, there is given tiles formalism, which allows to reconstruct all the invariants using one method. But I'll be using the integrable system formalism, which is, I guess, more convenient in this comparison.
Konstantin, you already mentioned this, but can I ask this question again?
Sure.
Is there a way to phrase it not as equality of numbers, but rather as equality of like homological field theories, or is
Right. So the problem is that so Liouville gravity, as is defined, is not a homological field theory. So I don't know how to promote it to homological field theory. It doesn't satisfy the usual relations.
and there's no gluing, or is it that?
Yeah, there is no obvious gluing.
Oh, okay.
So that's the problem, because if it were like homological field theory, we just look at 3-point functions and then we're done. But here, yeah, here there is some complication.
And the problem with gluing is because your Hilbert space isn't too big, is that, or what's the, or it's just not working, or
It's just not work. So like this yeah. Yeah, I don't know how to explain this better. It's just like just not working, because if you try to do some conformal transformations, like these correlation functions behave not as nice that you can split them.
okay.
So for example, if you think of 4-point correlation function as sphere, in homological field theories, what do? You can just degenerate one point to another, then it reduces to like two spheres meeting at one point, and then you can reduce this to 3-point functions. So in Liouville, what actually happens is that you get 3 different contributions for 3 different degenerations of your curve, of your sphere with 4 points, and then you get another contribution from the whole thing. So it's it looks, at least it looks a bit more complicated.
But I'm not saying topological, I'm saying homological. In homological theory, you don't degenerate it to 4 points. I mean, there is it just says, the homological says if you look at the locus where something degenerates, then, then all of that locus is reduces to 3 points.
Right, but yeah, I just don't see how, I just cannot do this, yeah, so cannot reduce this, so maybe. It's actually, yeah, it's actually, yeah, maybe I'll comment about this a bit more when I'll like show the comparison result. But okay, so how to construct this hierarchy? Maybe I'll very brief discussion. Construct this hierarchy. So there is a construction using Lux presentation very similar to KDV hierarchy. So I introduce the Lux operator, dispersionless, so Q of P is going to be P power Q plus some U alpha, I guess, -1 minus I, Pi, for I ranges from 0 to Q minus 2. And this is not alpha, this is Q. So the ordinary Lux operator is just Q of dx. So P here is, yeah, in order to get from ordinary hierarchy to dispersionless hierarchy, you just go to quasi-classics of all of your differential operators, let's say. So then we can define the flows of the hierarchy. So these guys are the functions of x and t alpha k. So x here is identified with t10. And the equations of the hierarchy can be written in the Lux form of the hierarchy are, so dq of p over dt alpha k. So so p is, of course, doesn't depend on these guys, but these u's, they depend on all these times, is a Poisson bracket of qp. And so we take a fractional power of this polynomial, which will contain, sorry, alpha over q plus p. So since the fractional power polynomial, it contains all the negative powers. And then we take only the positive powers in the expansion. Of q in the expansion. And the Poisson bracket is just defined to be Poisson bracket of p and x is 1. So it's really a semi-classical limit of a operator relation where we replace p with dx. And yeah, sorry for the notation. So those are different p's. This is actually not even a p, sorry, it's a k. So for example, to get KdV, to get a KdV differential equation, we just take q of p is p squared plus u is equal to u1, and take q power 3/2. And if we commute to differential operators, we get KdV hierarchy. So dispersionless KdV is dispersionless k dv is, so dq over dt is equal to this q over here commuted with q3/2 positive power. And if you write this in terms of for each coefficient of this p, it's equivalent to d over dt u is u times ux. So d over dux. For the full KDB, you have to add the dispersion term plus uxxx. Right, but I don't want to spend much time on this. So what I wanted to say is that this is, oh yeah, right. Maybe the last thing I wanted to say about this is that actually I from this Q operator can be expressed through our topological function via this Witten conjecture. Sorry, maybe I use more space. Right, so I, which depend on this T alpha K, and remember that X is T1, 0, is a second derivative of our free energy, so of our generating function, F1Q, 1 over Q of T alpha K, derivative with respect to dt10, dt I0. So this is like one of the ways to represent the Witten conjecture, generalized Witten conjecture in this case. And right, and exponent of f1 over q is called a dispersion style function. And it satisfies many relations.
I apologize. I somehow lost the notation. This 1 over q is just it's just notation. It's not a.
Yeah, it's a notation. It's a sorry. Yeah, it's
yeah. Okay. Yeah, that's fine.
Notation for spin curves because it's qth root of canonical bundle and 0, right? Again, if you replace dispersionless with actual and 0 with the whole sum, it also holds true. So this satisfies lots of relations. In particular, it satisfies the so-called Virasoro relations. And even more, in this case, it satisfies WQ algebra relations. Ln of, let's say, Virasoro relations looks like this. Ln f1 over q is equal to 0 for n greater or equal than -1. And so I'll write only L minus 1 because I will need only L minus 1. So is a differential operator in T's, which looks like this. T twiddle alpha k d over dt alpha k minus 1 plus some constant term 1/2 eta ab t alpha 0 t beta 0. So now I need to explain the notations a bit. Yeah, it's a sum. So this is a metric eta from our state space. These are just t's, and t twiddle are shifted variables t. So t twiddle alpha k are shifted t alpha k. That is actually a very silly shifted t alpha k's because there is only one shift. It's called the dilaton shift. T twiddle 1 1 is t1 1 plus 1. And t alpha k twiddle is just t alpha k otherwise. So and this is this equation. So L minus 1 exponent of F1 over Q equal to 0 is called the string equation. So this equation can be derived very easily, not very easily, but like fairly easily from the properties from the, let's see, from this formula. So it's just some relation on the topological numbers. But it plays an important role because in genus 0, so put here genus 0, string equation plus some boundary condition actually reconstructs you the whole function, the whole whole generating function, genus 0 generating function. Okay, and now we want to make some kind of comparison result. We introduced the quantities we need on two sides. So one of them is F Liouville Q over P of lambda mn, where there is P minus 1, Q minus 1 over 2 of these variables. And on the other side, there is this genus 0. On the other side, there is this topological gravity correlation function. So, sorry, partition function. Sorry, free energy. Anyway, which depends on Q minus 1 times infinity variables. So, first thing to notice is that this guy, I mean, it depends on a pair of numbers, Q and P. And this guy depends only on one number Q. And of course, there is this problem with a different number of variables. So let me solve the problem with absence of Q on the right-hand side, of P, sorry, absence of P in the right-hand side. So in order to do this, I actually need to fall back from my interpretation of this function as enumeration of curves, of some cohomology class over curves, and I actually need to go to interpretation of integrable systems, or given tile formalism, or like any other interpretation, because if you think about integrable, about Gelfand-Dieck integrable system, then this solution over here, which uses F1 over Q0, it is only one of the solutions of the hierarchy, but in principle, there are infinite number of solutions of the hierarchy, and under some genericity condition, they are all specified by choice of shifts in the string equation. So let me write this. For all generic solutions of Gelfand-Dieck hierarchy, so Virasoro relation holds. Ln exponent of f. Now I just call it f without any index here. Where the string equation is a bit different. So L minus 1 is summary of alpha and k, t twiddle alpha k, d over dt alpha k minus 1 plus alpha beta t alpha 0 t beta 0. So it looks the same, but the t twiddles are arbitrary shifts of times. So sorry, without brackets, t twiddle alpha k is t alpha k plus C alpha K, any constant. So all generic solutions of Gelfand-Dicke hierarchy I obtained solving the same system of equations where we shift the time variables in the string equation. I mean, in all the various order constraints, but it's not very important because for genus 0, it's only string equation matters. So the resolution of our problem is actually to take a different solution, take a different set of shifts. We define f1 over qp not, depending on the same set of times, to be so log tau of Gelfand-Dicke, Q's Gelfand-Dicke, for the following choice of shifts. So let us divide P by Q. So we can represent P as, let's say, if P is greater than Q, and P is some number S times Q plus the remainder. Then we choose the following shifts. Twiddle alpha K is TP0, S plus 1 plus 1. So we shift only one variable again, but a different time variable. So which is S plus 1's gravitational descendant of not of identity, but of a different element of our state space. And T twiddle alpha K is, should read it like this. P0 S plus 1 T alpha K otherwise. Okay, so the statement is actually that F Liouville Q over P of lambda mn is related with F 1 over Q comma P of T alpha Ks. So where this guy is not a generating function of enumerative invariant itself, but rather its analytic continuation, which is given by a different solution of KdV equation, of Gelfand-Dicke equation. So now we need to identify the parameters. Identify these two sets. And this is done using the scaling. So on the Liouville side, there is a natural cis-direction, because all the correlation functions depend on mu as just as a prefactor. So on the Liouville side, there is a cis-direction. So mu goes to C mu, and this coupling constants have to compensate the dependence on mu. So lambda mn goes to C power P plus Q minus Pm minus Qn over to Q, I guess, times lambda mn. And also for such solutions of Gelfand-Dicke hierarchy, there is a natural scaling as well. Same for the Gelfand-Dicke side. So we have a scaling T alpha K goes to C power. Yeah, I don't have, I guess, time to explain where this comes from, but it's really natural. So minus alpha minus K times Q over 2q times lambda mn. And we want to, we could identify not just like, two functions of a bunch of parameters, but we could think of them as two functions with a C direction on them, so with some scaling. And then the identification becomes a finite dimensional problem. So naive identification is just, F Liouville Q over P lambda mn is F 1 over QP of T alpha of Mn K of Mn, where this guy scales as lambda mn. Sorry, what did I say? I wanted to say this, so it's equal to lambda mn. So in other words, we perform the coordinate change T alpha k is equal to lambda m of alpha k n of alpha k in the right hand side, where they scale the same. However, this turns out not to not be enough, because under naive identification the numbers don't coincide. Under this, the fusion rules, so fusion rules of CFT of minimal models are not satisfied. And let me recall what it is. So let us return to gravity correlation numbers. To our examples. Yeah, here. So we have 3-point gravity numbers, and they are just products of these fusion rules, so constants 1 and 0, multiplied by some very simple and non-significant factors. So the point is that we can use these fusion rules to fix this coordinate transformation. So proposition, so which was done in many papers like Belavin, Zamolodchikov in 08, Belavin, Dubrovin, Muhamedjanov. In 13 by Belavin, in like 15, etc. That up to 4-point correlation numbers. In other words, up to fourth derivatives of these functions. The fusion rules. So which is, so we take the topological quantity, F 1 over topological gravity quantity, and 1 over QP of T of lambda. And then we differentiate it with respect to lambda 3 times to get 3-point correlation numbers, for example. Should be proportional to fusion rule. So the fusion rules determine polynomial C star preserving coordinate change. So T alpha k is lambda mn plus some constant times lambda m1 and 1, lambda m2 and 2, plus etc. So some So the coordinate change between those guys is polynomial of weight. So C star weight same as weight of the left hand side. And after this identification, to this coordinate change, we have these two sides. So these two sides coincide. Up to 4 points on a sphere. F 1 over Q comma P naught of T of lambda up to fourth derivatives. Okay, so this is, so far, this is one of the main advances in these theories and one of the main conjectures. Yeah, it's not much, but still. So,
Question.
once again,
So in both kind of topological gravity and also in matrix models, things like string equation usually not so difficult to show. Is there
that's right.
Is there some way to see that string equation on the what should be the string equation on the Liouville side?
Yeah, that's a very good question. So the problem is that okay, let's look at string equation and just try to to pull it back to the Liouville equation using this equality. So the problem with this like we're thinking that when we pull it back, so there are this very complicated polynomial coordinate change. So they look kind of like orthogonal polynomials. They're built of orthogonal polynomials, in fact. But the problem is that after this like pullback, the string equations becomes a complete mess. So again, so far I don't know how to interpret this. So in Liouville equation, in Liouville theory, there is some analog of string equation, which is, so in Liouville, like the closest analog is probably the following. So we take some correlation, and then we insert like the kind of the identity operator. Then this is reduced to the correlation, the k-point correlation, but as opposed to string equation, it more looks like the dilaton equation. So it's OMK and K times some prefactor. So it's actually it has a bit different nature, like the simple equation which one can get in Liouville theory. And if we take just string equation itself from, so this is how you derive string equation, right? So you take any correlation function and then you add insertion of just identity element of your state space. And what you get is usually some more complicated right-hand side, which allows you to basically reconstruct your genus zero theory. In Liouville, if you take identity, then the equality is too simple. It's basically the scaling relation. So it's dilaton equation instead. And and if you just pull back string equation using this equality, then I don't know. It looks, it's
okay, a different question then. So in integrable hierarchies, you can in principle say, well, I study kind of one equation, and then it commutes with a whole bunch of other transformations. And I may or may not specify which coordinates do I use for this transformation. I can say, well, whatever. It has many commuting Hamiltonians. I'll kind of take them all and I parameterize them in some way. There's some choice of coordinates. Is there some case of this equality where you can say, well, there is some somehow can you say that this this is equivalent to just proving something with, and so in other words, the way to say it, in integral system, you can say, well, I've proved something for the key DV itself, say, and then there's by some general nonsense, I have a whole bunch of commuting flows. Well, I don't know what they are, but I know they commute with KDV. Is there some kind of small case you can similarly say, well, this can be reduced to just showing some relation, and then the rest is just, well, it's just some bunch of constraints that commute with the constraints I've already proven?
I think actually. So yeah, let's say it like this. So I guess we can do something like this, but the major problem is that so far there are no. Yeah, actually, I didn't think about this enough. So the major problem is that so far we lack relations on Liouville side, and like how we're approaching this problem is basically like try to do something in Liouville, and then we get like some, the small things like a few correlation numbers on like spheres or disks or like a torus, and then we try to and then on the integral systems, like from the other hand, there is so many machinery, and then we just use this machinery to compare. But but that's a good point to try to get something like this on Liouville.
I didn't want to steal your the drum roll, but when you draw the box, you draw the box. Now you're gonna say that's the main theorem.
Yeah. In principle, it would be like this, like kind of a dream. In this case, it is some structure on the Liouville side, which which basically allows to reconstruct all of it. And if we have this structure, then we can just compare two structures abstractly, without like complicated computations of some concrete relation numbers.
I guess what I was trying to say is that since you have some unspecified change to variables, then or at least maybe not specified for us, at least unspecified for us change to variables. That sounds to me like a case for the situation when you prove some kind of deformation theory argument. You prove there's two structures coincide on one point, and then you in principle the extent to some bigger parameter space, but how exactly that parameter space is identified, that is, somehow it's to be determined by something else.
Yeah, that would be great. That's actually like so the problem, the main problem with this approach for now is that like we don't have the structure on the Liouville side. That's kind of this, the point which stops us. But yeah. So I guess I'm kind of over time, but let me just say in words, maybe write like one sentence about the other sides to this correspondence. So so far I only talked about spheres, like up to 4 points, which is not very intriguing, let's say. But actually, like there has been done some work on torus, which I'm not completely familiar with, 1-point function on torus, but which I'm more familiar with, which I actually did quite a lot, is this correspondence on a disk, on level of disks. So a few people developed a theory analogous like topological theory for counting disks in these examples. Like in KDV, I think it was done like by Pandey, Solomon, Tesler at like 14. And then for R-spin, it was done in 18 by Burak, Mediclator, and maybe Tesla as well. I don't completely sure. Anyway, so there was a theory of disk counting developed for the topological field theory. And what's nice about the counting of disks is that the Witten's conjecture also generalized to the disk counting. In other words, the generating function of disk invariance can be written in terms of some data of integrable systems. in particular, like we can write disk 1-point Balkan invariance in terms of 2-point spherical invariance, Laplace transformations of two-point spherical invariance. It's on the topological side, and on the Liouville side, there is also a developed theory of open theory. The problem with that, it's even more complicated than the closed theory because one has to take care of boundary conditions, and the bootstrapping of conformal field theory becomes more complicated in presence of boundary. But something still can be done. So maybe let me write one function. So disk 1-point functions in Liouville. So in boundary functions depend on this scaling parameter mu, in fact, in a very non-trivial way. So they look like some scaling factor in mu, and then there is a Bessel function. So it's hard to call this like this 1-point constant. It's because it depends on this parameter in a very non-trivial way. So it's L square root of mu. There is some argument of the Bessel function, and this is length of the disk. So this was obtained by Fateev, Zamolodchikov in like 01. And using the formulas of topological theory and ability using kind of Witten conjecture to represent them in terms of spherical correlators, some simple quantities we can compute. Like me and Volodya Belavin managed to, a couple of years ago, managed to show that the dependence using the same coordinate change, using the same resonance transformations, if we replace these guys with, disk 1-point functions in this case, we can recover the dependence on this disk length and cosmological constant mu. So this is what has been done in this correspondence up to the best of my knowledge. And the whole
disk
point
length
of the,
means it's the radius. What does it mean, disk length?
Boundary length.
Boundary.
So the disk boundary. Yeah, that's right. Disk length sounds a bit. So it's Laplace dual to basically. So yeah, maybe I won't say anything else in this regard for now. Yeah, but the whole point is that so there is some correspondence, which certainly should hold because there are lots of. So in this relation over here in particular, since we have infinite number of minimal models Q over P, it gives us infinite relations which hold true, and also like the disk case which supports the same conjecture. So it's natural to conjecture that actually for any genera, these theories should be related by something like this. And yeah, the main thing. So I'm not working on this very intensely now, but the main thing I'm working in this area is to try to get some nice structure on the Liouville theory, try to get some recursion relations, try to get some kind of string equation, to try to get some relation which allows us to compare these quantities like in a more clever way than just comparing numbers and computing these coordinate changes. Yeah, but yeah, there is lots of nice things hidden inside. I guess I'll finish with this. Thank you.
Questions? Song, do you have a question? You raise your hand.
Oh, something in chat? Oh, no, I see.
Yeah, something in chat. Thank you.
Mm-hmm.
And,
yeah, there were a few questions during the talk.
Sorry, can I still ask the same kind of
Sure.
the same question again?
Sure.
So suppose I have a whole bunch of points on the surface, on the, and then I have some local operators, let's say comes from matter minimum model, and I also have my my Liouville vertex operators, and then they each have their own conformal transformation law. But
Right.
I think you said that you adjust for every point you find the Liouville vertex operator, so that together this looks like a differential form on the moduli spaces.
Exactly.
Right?
Yeah, this is precisely how it works.
And so then the integrand is kind of like a differential form on the moduli spaces of curves, right? Is it not?
Yes, it is.
And then you say that if I try to restrict it in some way, maybe take the residue along the, so what would mean to have gluing? Is that somehow restricted to the boundary? I'm not sure, maybe take residue at the boundary, or somehow restricted to the boundary. And it should, that should reduce to the same thing with, fewer points, small lower genus and so forth. And you say that is not obvious, or that is not true, or
that is not obvious. That is not obvious.
Okay.
So yeah, so far it didn't, like, and people didn't. But I guess also I guess also we see there is
because
lots of
people
stuff.
have hard time summing over intermediate states, as if you have a node.
Yes, because the intermediate. So the problem with these correlations is that as they are written, the intermediate states in like minimal model and in Liouville are like completely don't talk to each other like at all. Okay. And since it's a product of these two things, which transform like a form only when multiplied, and intermediate states like don't talk to each other, this is so. Actually, the recursion which was obtained, like for these 4-point functions reduced to 3-point, I mean, it's not recursion, but this reduction from 4-point functions to 3-point functions. So it was obtained precisely like by, by some equations which allowed to match together these intermediate states in Liouville and minimal models.
I see. So the main issue is to make actually the two Hilbert spaces actually don't really talk to each other. Is that somehow
exactly.
in a way that? Okay, so it seems like an actual physical problem, not just kind of a math problem.
Yeah, but that's right. Yeah, it's not just a mathematical problem, but but it can also be done mathematically. So because it's Liouville and minimal model, and both of them are nowadays have definitions. So.
All right, and then the second question I had about this proof of the spectrum. So you can say, that this is okay. So if you have like an action, presumably you can define the correlation functions, by some kind of expansion. Presumably you can define them somehow. And then the statement about the spectrum would be saying that, like a lot of these insertions, unless they satisfy some condition, in fact, like go to 0 or something like that.
No. So the point is that actually, like there are a few things hidden here. So in particular, these Liouville dressings, which enter these equations, they do not belong to the spectrum.
Right. But I was saying I thought the statement about the spectrum was before any matter was introduced. Was that,
right.
Or that just doesn't make sense, or
right? No, it does make sense. But the point is that so what is the statement? Like physical statement. Physical statement is that if we like take Liouville fields and try to compute this correlation function using bootstrap, so using operator product expansion using our spectrum, then the bootstrap is well defined and gives these Liouville correlation functions. So this is, and also this spectrum is like normalizable in some sense. So there is some the 2-point functions, they are given by this reflection relation. So, and as far as I know, at least like on the physical, of course, like mathematically, I guess bootstrap is not proven for Liouville. So because there are people like in our department as well who are working on proving bootstrap, but yeah. So this is the statement.
But so maybe can I try to ask the same question again?
Sure.
So first, I mean, it's one question. Once you wrote once you wrote down, so you can principle, you can write some Virasor representation and you can imagine some 3-point constants, but then you can actually fail to construct the actual.
That's right, exactly.
Yeah, and so there's a point, there is a logical point of saying, I can, from this data, I can construct a well-defined and non-self-contradicting theory. That's one thing. And that is, okay, and this you said has been done, right?
Yeah, physically.
And then another question is that if I already have some definition of a theory, such as by some diagram expansion or something or whatever, right?
Then
and
it
I can
coincides
ask,
with this.
then I can, yeah, exactly. I can write like an evolution operator, and I can ask what is the actual spectrum of that evolution operator, right? So I can, and so then, and so then it then becomes some result that the actual spectrum of that operator is what you say it is, and that has also been proven, or is that?
So this is what like guys from probability in our department are doing. So they're proving bootstrap, and like they proved it in some cases, and in some cases they're still proving it in the sense that they have this definition of the Liouville correlators, which is like basically probability version of the path integral, which works rigorously. And what they're trying to prove is precisely that these expressions are equal to the bootstrap integrals, so to the SOP integrals. And they are more or less successful, I think. So there are some technical issues, but.
Okay, cool. So those are the talks already heard.
Yep.
Okay.
What Guillaume told on this seminar.
Yeah, Guillaume.
Last fall.
Okay. All right. Other questions? Well, if not, thank you, Konstantin. That was great. And,
thank you.
To be continued next week.
Yep. Goodbye.